Cody Trevillian. I am from Oakland University. I'm a fourth-year PhD candidate there, and I am quite excited to present this work to you, the interferometry of single Magnon decoherence mechanisms. So first, we should discuss what exactly the motivation for this work is, and that really is the advent of these single Magnon sources. These single Magnon sources and fabrication methods that can yield strong coupling rates, taking our low damping YIG material and putting it onto superconductors. And so that really gives us great leeway into the use of these single Magnon sources. So first, just to get everybody on the same page, what exactly are Magnons? Of course, Magnons are quantized spin waves, and Magnons are quasi-particles. And this is important because being collective magnetic excitations, they will behave a bit differently regarding single quantum decoherence processes as compared to something like photons. But we can take some inspiration from the measurement methods that we use to study photons. That is, we can use this so-called Mach-Zehnder interferometry, and I call it a spatial domain interferometry of photons, wherein you take a laser, you put it through a beam splitter, you have two sort of adjustments of your interferometry path arm lengths, and then you detect the output at your detector screens shown here. And so we can really define a pretty analogous operation going from studying photons with lasers to studying magnons with qubits. And these superconducting qubits are the things that magnons, being these quantized spin waves, can couple very well to. So to do this, we should build a model to exactly describe what this measurement scheme is here. It's important that I should say that initially with this measurement scheme, you would excite quantum in your qubit, and then you run this entangle pulse operation, which I will explain in a moment. And then after some time, you unentangle it. And if everything went well, and perhaps you didn't allow it to interact to freely evolve for any amount of time, your input in your qubit will be completely output into your magnonic resonator, your magnonic subsystem, and you would measure nothing in your qubit. And so to realize a system like this, we should take some inspiration from previous experiments wherein you have some sort of a superconducting resonator line here, and you can place a magnetic element right on top of it. You control the resonant frequency of the magnetic subsystem by just changing this magnetic field here. And we can describe it with a Hamiltonian as shown, wherein we're just describing this coupling rate between the Magnon and superconducting subsystems with this kappa term here, and we have the resonant frequencies. So nothing too crazy just yet. But what we can do is allow this system to interact for some amount of time, this tau tangle that I show here, where we can realize a what I would call a tangle pulse operation, wherein when the quantum is in the qubit, we run this operation, and now half of our quantum of energy is in the qubit subsystem, and the other half is in our Magnon subsystem. And then what we can do is allow this system to interact for some amount of time tau in such a way that we are very weakly coupling the two subsystems. After some amount of time, then we again bring the subsystems close together in frequency, causing them to strongly couple. and unentangle them using the same tangle pulse operation. So I show this in and this out, and we see here that this operation would give us an entangled state, and then you unentangle it. Now, as I had said before, this system is described by a Hamiltonian, but because we are describing the decoherence mechanisms in this magnonic subsystem, we need to use something called the Lindblad equation, wherein we can describe something called the Lindblad dissipator, and we can take into account some jump operators that describe our single Magnon decoherence mechanisms. And so this measurement scheme is then designed so that when this dissipator is 0, i.e. I have no decoherence mechanisms present in my system, then the output of this measurement of the magnonic subsystem after the whole interaction measurement scheme is complete would be 1, and the final qubit population, which is actually what I'm measuring, would be 0. And so then anything that goes on due to these single Magnon decoherence mechanisms during my free evolution time tau would be describable in this final qubit population. So I can just measure the qubit after this measurement scheme and be able to hopefully understand better how these single Magnon decoherence mechanisms work. And so in doing so, I describe two sort of more common decoherence mechanisms, these Magnon amplitude damping and Magnon phase damping. So you can think of this as just a normal dissipative interaction, and this phase damping is sort of a dephasing. And I describe them with a set of Lindblad jump operators, and you can see them described pictorially here with these Feynman diagrams. And so you have a Magnon that hits some inhomogeneity and perhaps scatters directly into the spin lattice, or you can have a Magnon and a photon that come together, and we get this phase damping or dephasing interaction to occur. And this Lindblad dissipator is associative, so I can just put in my two jump operators and be on my way to simulate this. So let's look at some of the results of this. So this measurement scheme, then, I would fix the frequency gap and vary the free evolution time tau. And so this frequency gap is the controlled during the free evolution time. And what I see is that at some fixed frequency gap, as I vary the free evolution time and there's no decoherence mechanisms present in the system, I sort of get this expected oscillation between no population measured in my qubit after the measurement scheme is ran, or I will measure it 100% of the time. So the entire population of the quantum is still in that qubit after the measurement scheme. But when I allow some sort of a damping noise to be present in the system, then I get this sort of decay, as one would expect, in the measured final qubit population. And when I allow there to be some sort of a dephasing noise to be present, the average of the final qubit population doesn't change, but I see that, of course, I get this phase damping behavior as one would expect. And so the interesting thing is, when we have them both present in the system, we can see that the average of the final qubit population would depend on these two different decoherence rates. But with a fixed frequency gap and varying the free evolution time, we sort of lose our ability to measure a good amount of data points once we get to a larger free evolution time. So what we can do is instead fix this free evolution time and vary the frequency gap, which a measurement scheme like this would be a lot easier to realize experimentally than the previous one, just due to the point that I made introducing it. And what we can see is that by running this for some fixed free evolution time and varying the frequency gap, I can phase shift my way through all of the relevant behaviors of my final qubit population. That is, I still go from measuring nothing in the qubit to measuring the whole quantum in the qubit 100% of the time. And the interesting thing is then when I include the decoherence mechanisms in the system, I can just, I don't sort of lose the ability to collect more data points. It's a lot more apt for collecting this data and sort of reducing my error in the end. And so by inspecting this in some way, I can take this average of the final qubit population, remove the parasitic impact that the Magnon amplitude damping noise applies to it, and then I can pull from that the Magnon dephasing noise. And so by just measuring this final qubit population, I can determine the decoherence rates separately, and this is very interesting to me, and I hope to you also. So this work is just sort of getting started, but it's a relatively simple measurement scheme for these single Magnon decoherences using some dynamically tuned Magnon resonance. And the important thing is that this can be realized today using available technology. And as we venture into use of single Magnon sources, understanding this quasi-particle decoherence at these single quantum levels is really important for us to be able to utilize these finite Magnon number states. And I'd like to say that a better understanding of these mechanisms may lead to something interesting, such as development of this quantum magnonic error correction methods, as we want to apply them to our magnonic quantum computers. So thank you for your attention. And if you have any questions, please kindly let me know. Thanks.
Thank you, Cody, for your presentation. If anyone has a question, you can raise your hand. Really nice work, Cody.
Thank you.
We have a question from Patricia. What kind of materials would be interesting to study with this technique?
In terms of what kind of magnetic materials?
Yeah.
I would say my preference would be to use YIG because this is the sort of ideal low damping material. It's like the magnetic community's silicon, right? So the more we understand about that, using these new fabrication methods, advancing our way towards these YIG-on superconducting systems, I think that would be the best thing to do.
Yeah, I think Patricia, did he answer your question? I think so. So thank you, Cody.